going to leave that alone. But let's talk about Poisson's ratio, because we're going to use Poisson's ratio. And what is that? So if you're a rock squeezer, and you take a piece of elastic material and you put it and you want to analyze it for Poisson's ratio, what you end up doing, if you're at Cornell working with Don Turcotte or some of his students, you take this material and you put it in a vise so as to restrict the X dimension from changing. Okay? Then you take a C-clamp and you stress the Y dimension. So Poisson's ratio is defined as the lateral strain, the change in Z, divided by the longitudinal strain from your C-clamp for an applied longitudinal stress. That's the definition of Poisson's ratio for the rock squeezing community. And they'll prick their ears up when you say that. Now they're following your presentation. And that's the civil engineering community, structural geology, anybody that squeezes rocks. That's fine. There's another definition for Poisson's ratio that uses compressional and shear wave velocities and keyword nothing else. And you'll see it expressed many different ways, but here's VP over VS squared and all this stuff with some algebra to get Poisson's ratio. Same quantity, same value. Okay? All right. Now in practice, so here I did a little modeling, and I've got a propagating disturbance going out through a geological model, and I hit this boundary at that star. And now I'm going to propagate back a PP data set and a mode converted shear wave PS data set for the Z phone. That is to say, I'm out there with two component size models, just like Garota's written about in Domenico and Danbaum's textbook. And for the PP data and the PS data are both recorded on the, according to this, the vertical geophone. Well, don't believe it. It's not right. Similarly, for the radial geophone, it says you're going to get a PP event, shown here, and a mode converted shear wave event, shown here, but that's not what happens. What happens is this. The model didn't have any near surface elements to it. And so what that says is these events are coming back to the surface, and they hit this array and they show up on both events. What happens, in fact, is that these PS events or PP events come back to the surface and are bent severely to the normal by the near surface. And what happens then is there's total isolation of the PS data on the radial and total isolation of the PP data on the vertical. So when you're sitting in the observer shack, and we used to play back the evens or the odds on a piece of paper and look at it, I would look at really good PP reflection events with absolutely nothing on the radial traces to show their presence. And I would look at the mode converted shear wave analog on the radial, and I would see nothing on the P wave. So there was total isolation of the two events. So just the opposite of the modeling. So your modeling is no better than your model. If you don't include the near surface, you may have this sophisticated model, but it's giving you wrong information. So that's a good example how the experimental data for a 96-channel instrument is going to isolate the PP from the PS events. Okay. Now, as Tom Rape said, Sean, you remember him saying, he says, if you're going to do mode converted shear wave, there's a certain amount of pain. So I'm going to show you remind you of some of the pain here. For PP data, your standard PP data, you end up with field files, you convert them to common midpoint gathers, and you have traces that look like this as a function of source receiver offset. And they create nice hyperbole, and you can move them out and do all the stuff, right? What about for mode converted shear wave? So you go into your header words and you sort, right? And what you're sorting is to have the source receiver, here's source receiver, the traces in the middle, right? And of course the answer is no. Because go back to your Zopert's equations, you'll quickly see that what you'll get is a smearing on the surface as a function of what your source receiver offset is. But if you'll think about that for a minute, a couple things, and I'll leave it alone. Number one is, that's exactly what happens for standard P-wave data in dipping areas, so it's not like the end of the world. And the other thing is, you know, we got into header words back then. You know, the analogous to what you do your header math on your Promax. We would go in and mess with header words, and what we found was, if you assume that VP over VS was 2, which is a nice round number and pretty common for basic correction, that this separation B turns out to be 1/6 of the source receiver offset. Piece of cake. So we could go into the header words and modify the header words to accommodate that. Easy to do. For a simple assumption of VP over VS, which 2 is a good round number. You know, I mean, it'll play around that. But so what that would do is be getting it closer. But if you do nothing at all, you're still okay. It's kind of like doing velocity analysis with field files. You can do it. You just get an averaging technique, right? No problem. Okay, a little magic here. And this is, you'll see this in Garota's last figure on his stuff. This is what we were doing. The man's name is Chitty Babu Chitnini. He worked for me. He was an applied mathematician. He's now dead. He was a very smart man, and so we came up with a schema that was pretty much replicated at the Kansas Geological Survey and Company General of Physique and other places. And what it amounts to is you take a shear wave trace and you simply stretch the P wave trace in time to fit the shear wave trace, a nonlinear stretching. And the residue from that stretching function is VP over VS as a function of P wave time. That's in the literature. I can talk about it now. It used to be top secret at Conoco because we had a leg up for a while on people. So what happens is, this is what you call a real attribute. Because what I've got, actually I've got VS over VP. I'm going to lie to you and tell you it's Poisson's ratio, but it's the same thing. What I'm able to do is to put a color overlay of Poisson's ratio or VP over VS or VS over VP, whatever you want to use. It's all the same thing. I can put that over the top of my P wave section, and that's what a gas field looks like. Okay, now this is circa 1982 we're doing this. Okay, we have a P wave section, and we have an attribute actually measured Poisson's ratio over the top of the P wave, and that happens to be exactly where a gas field is. So you say, well, why is Poisson's ratio little bitty or VSVP very big, or what's going on there? And what it amounts to is, whenever you replace the fluid in the pore space with gas, the P wave has no real advantage over the shear wave. And so what happens is the VP-VS ratio starts looking like a real hard rock. Normally they get close to each other when you're in a highly rigid rock. But in fact, if the pore space is full of gas, the P wave has no advantage over the shear wave. And so again, the ratio shortens up. So in sedimentary rocks, when the gas is replaced, it replaces the fluid, Poisson's ratio will get to numbers like 0. They even get to be less than 0, and you say, wait a minute, we've gone into Never Never Land. What do you mean less than 0? What that would mean is if I take a material and I push on it, that the other end puckers and goes the wrong way, it doesn't push out, it puckers in. And the answer is you can have 0 Poisson ratio numbers. Take a dry sponge and poke on both ends. This dimension here will pucker in. So if you have a very porous, dry material, even a sponge, you can physically check the mathematical possibility. Where it breaks down is the square root of 4/3. The P and the S speeds cannot be any closer than the square root of 4/3. Anything bigger than that is okay physically and okay with physical analogs. So Poisson's ratio can be slightly negative and be indicative of natural gas in a system normally dominated by fluids. That picture was made when I had black hair. So 1981, 2, 3, and that's not some attribute that doesn't mean anything. That's a real attribute measured from the data itself. Keyword measured from the data, not estimated. Okay, that's half the story. And good place to take a question. That's half the story. What did I just say? It says that Poisson's ratio, or VP over VS, or VS over VP, is all the same thing, is a good indicator of lithology. Now we're going to talk about the pore fluids, and so go ahead.
Okay, maybe you were about to just go right to it, but I was going to ask, so if it's a gas structure and the Poisson's ratio is around 0, if it were a liquid structure, would you be able to tell?
Poisson's ratio for a sandstone would be like a quarter, 0.28, 0.29. Carbonate, 0.32, 34. So Poisson's ratio has a nice variability about it. And if you're dealing with sedimentary rocks with pore space and matrix, the carbonates hang out about 32, the clastics hang out about 25, and that's how you get the isolation on VP over VS. And that's what Pickett showed in 63, and now the current discussions continue to show that. But if you replace the brine with gas, it's not that the shear wave catches up with the P wave, it's the P wave drops back to be like a shear wave. But they get close to each other again. It's not that the shear wave caught up because it's rigid, it's because the P wave slowed down because it's all this gas. And it's 3 orders of magnitude different, so that bulk modulus is driving the equation. So 0 numbers for Poisson's ratio are pretty realistic for measured Poisson's ratio for a material for which you have both body waves. If you throw in density, you got the entire elastic constants that you can put as a color overlay. Yeah.
And if there were liquid filling within the void space, and the ratios would increase.
Mm-hmm. Yeah. Let me go back to that picture. Actually, this turns out to be VS over VP increasing downward, so that's a big VS VP. Am I saying that right? Yes. A big VS VP should be a small VP VS, which would be a small Poisson's ratio. Yeah. So this pink color is big VS over VP, which would be a small VP over VS, which maps onto a small Poisson's ratio. And so I say again, if Poisson's ratio getting towards 0 is not uncommon for a gas-filled sedimentary rock that was normally brine-filled. So here's your brine-filled rocks. They're out here someplace, looking normal. Here's your gas field. So if you have sandstone, it's about a quarter. You have carbonate, it's about 0.32. And then as you move towards other materials, it's not a simple one-to-one mapping. If you went from sandstone to quartzite and you had no pore space and it was really rigid, you'd probably get to numbers like 18. But it would not be the P wave slowing down, it'd be the shear wave catching up, because the rigidity modulus would start to play a bigger percentage of the velocity change, because the bulk modulus would be incapacitated. No porosity. Yeah, yeah. So the mapping is complex, but clearly if you're in sedimentary rocks and you see something that has a low impedance, that's a good thing. If you see Poisson's ratio getting near 0, that's a good thing, because you're indicating that you've got hydrocarbons in the pore space. That's what it means. Okay, let's talk about bright spots. We're switching from